So there is that side.
Was this recorded?
Yeah, I'm recording now.
Like your statement?
Yes, it was. Well, I normally edit the first few minutes off anyway, so I'll make sure. They know. It's not. There's no secrets. All right, that's about right. Okay, so what have we been doing the past few classes? What did we do last week? Quasi-geostrophy, planetary geostrophy, so reduced dynamic systems. And we also have shallow water equations, which is another reduced dynamic system. We have 2D, which we're going to use a lot, which is a lot like the shallow water equations, except the incompressible shallow water equations. So we have a bunch of assumptions going. We have a bunch of different equations of motion. And the reason why we need all those pieces is that we're actually going to start talking about turbulence and instabilities within those systems. So how do we think, how do you think that impacts the kinds of instability or turbulence that we might see?
What do you mean?
So why would we choose to do the instability in, say, the quasi-geostrophic system rather than the full Navier-Stokes system? Like, why is that even part of what we're learning how to do? What do you think? What do you think is the strategy there? We talked about this a little last time, but let's come back and start from there, because we're going to do quasi-geostrophic instability this week.
I mean, one thing might be like if you want to do computationally relatively inexpensive modeling, instability at different scales of modeling will affect. Like if you have different approximations that you're using at different scales, then instabilities might affect. From one scale might affect a different one.
Yeah, so there's an efficiency factor, and the efficiency factor. So this week we're talking about instabilities, which is primarily an analytic theory, and so it's going to make our lives a lot easier that we have only one type of instability to worry about at a time. So when we do the quasi-geostrophic ED problem, which we're building towards, the ED problem is kind of the simplest baroclinic instability problem. There's only one class of instability. If you do the Navier-Stokes or Boussinesq equation ED problem, there are 4 that I know of, and probably more under kind of small tweaks away from that system. So it makes our lives easier because we have only one thing that we've simplified the possibility, the classes of instability. But what does that mean about the world? So how do we interpret that? So we did reduced dynamics under a particular set of assumptions. We simplify the instability problem. We find only one kind of instability at a time. How do we interpret that when we go back?
If we change our regime of non-dimensional numbers, then instabilities will shift or change, or they might be completely different.
Exactly. And so when we have, say, the quasi-geostrophic baroclinic instability, we're imagining that that's the most important one near the deformation radius, say, but it might not be the most important one overall. So we'll have to have this back and forth, thinking about, is it the big ones that matter? Is it the little ones that matter? Is it the fast ones that matter? Is it the slow ones that matter? Is it the ones that extract the most energy most rapidly that matter? Is it the ones who have the largest kinetic energy that matters? So there's a separate assessment of what these instabilities are like, but simplifying our equations first and then doing the analysis or doing numerics makes our lives a lot easier, because we can make progress to understand them because it keeps it minimal, but we're always thinking back to the original equations that have a lot more stuff. And sometimes, I'll show an example at the end of this week, we're able to go back to the original equations and study the same problem numerically in the original equations and see that the thing that we thought was dominant is actually indeed dominant. So that's the game. All right? So we're going to talk about Kelvin-Helmholtz instability, which is almost so easy that you forget that it is something that's hard to think about. But that's an example that we're going to keep coming back to as we go into parallel shear flow, which is a generalization of Kelvin-Helmholtz, and then baroclinic instability, which is a further generalization of flow classes away from parallel shear flow. So this is kind of a 1D problem. This is sort of a 2D problem. This is a 3D problem. So we're building up in complexity of the geometry we're considering as we go. And then the ED problem will be one that we're going to talk about, and then necessary conditions is a theme that comes in from instability. So how many of you have done instability before? Have you ever seen this in a fluids class or anything? Yeah, some. So the nice thing about starting with the Kelvin-Helmholtz is we can think about what it means from the beginning, and it's a clean problem. So we talked about this even on the first day, actually. So here's the situation we're imagining. What if I have a shear so that part of my fluid is going this way and part of my fluid is going this way? I've just imposed that flow as the initial condition. What do you think is going to happen? It's going to start swirling somehow in the middle. Something's going to grow in between these two, and it's going to start mixing in the middle somehow. Does that make sense to everybody? If I'm in the bathtub and I push like this, you get little swirly things in between. Like, that's the problem we're talking about. This is a very simple one because it assumes that there's no variation in this current and no variation in this current. There's only one point where it jumps. So it's kind of the simplest case, and then we're going to make this flow profile more interesting as to how we're going. So the instability problem and in itself, or sometimes it's called the stability problem, because the more powerful result is the not instability case, as we'll see. The idea is that, well, yeah, it becomes turbulent eventually, but turbulence is complicated, and let's not worry about that. Let's do just how big are the things that start the wiggles. So we're just going to do a linear infinitesimal perturbation problem to this interface. So what if we start to get a wave-like mode along that interface? Does it grow? Does it decay? What does it do? That's what instability is about. Or is it just stable? Does it just stay there? And so when we go to full turbulence, we're actually not going to be able to really use Fourier transform like this because all of the modes are blended together. So the homework from last time, where we did the Fourier transform of the QG, the geostrophic adjustment, is kind of a classic problem. And the key was, this is a linear system. All the modes are independent. Almost by definition, what's different about turbulence is all of the modes are interacting. So this is a weakly nonlinear. Modes are all separate. That's what the instability problem is. And the difference between instability and turbulence is what comes next, where all those unstable modes start interacting with each other and transporting stuff from wave number to wave number. Okay? So we're just going to touch on instability. We're not going to do nearly as much detail as Valis does because we want to get to turbulence. That's actually what I want to talk about. But how big the turbulence is a question we still have. So there's nothing really in this problem that says how big should how big is the turbulence going to be? Like, what's the biggest eddy that's going to form from the front? There's no natural length scale in this problem. So how do we even think about that? That's what we want to start heading toward, is that kind of thinking. This problem is unfortunately too simple to really have a natural length scale, so we're not going to get a good answer here. But as we add on layers of complexity, we're going to see that length scales and time scales are popping out of it spontaneously, and that's going to help us think about the instabilities and the turbulence in the real world. Does that make sense to everybody? Okay, so here's how the math goes then. Just like the homework last time, we say, assume that any variable, any flow variable you want is a Fourier transform. And so you can do this, and there is actually a real part here. So this is complex, this is complex, this is just the cosine part that's coming out. Or well, I guess it's the cosine times the real part plus the sine of the imaginary part of that coefficient. Because this is a linear instability problem, it's really easy to forget that there's a real part there because it never comes back in the end unless you're trying to match initial conditions. But if we do nonlinear theory, this is really important because without this you get the wrong answer. You have to have the real part. Only the real parts are talking when you make the nonlinear product. We just never have to really worry about it here, so it's important, whatever. Well, you'll see how that goes. Okay. So this is a 2D problem. So Vala sets this up in a purely 2D flow, incompressible 2D flow. So let's even write out the equations. So what do we have in 2D? We have du. Let me write the other way. d by dt of u plus u, and I'm writing u like Ballast does for 2D, equals minus gradient of pressure over rho naught. It's incompressible, so there's just a density there. So where does that thing come from? How do I get to that bit of business? How can I get a Laplacian of pressure out of this equation?
Take a gradient again.
I can take a divergence of this whole game, d by d, and this one's easy. But this one, all right, we can move that inside, so it's like the divergence, it's the gradient, it's the double divergence of u like this, right? So one of these is going with one of them is going with the other one. Yes? Or I could have written this as the vorticity form, but in either way, this guy vanishes because of incompressibility, and so, oops, the only one we get is this guy. Okay, so that's the divergence equation. The other important equation is the vorticity equation, which we would get by taking the curl of this equation. So let's see how that goes. We get the vorticity, we get the curl here. What happens to this term? If I take the curl? 0. And then this one gives us that complicated thing where there's vorticity dotted into the gradient of u plus u dot gradient of vorticity, right? This is the tilting and stretching terms. We'll see let's hold on to this for a moment and see what happens to it. Okay. So the next thing we want to do is we actually want to linearize around this background state. The background state can be finite amplitude, but we want small perturbations from it. Okay? So small perturbations. So u equals u plus u prime. And we can take the curl of that equation. So we have zeta equals something plus zeta prime. So what's the curl of this? It's 0 everywhere except for maybe at the interface there's something crazy. Let's leave that aside. It's going to be 0 everywhere away from the interface. So the system we're going to take is we're going to talk about below and above the interface, and then we'll match it back to the middle and figure it out. So we don't even have to know what the vorticity is, but let's talk about the vorticity equation away from that interface. So in that case, this is 0. And so, okay, so now let's go back to here. What have we got? There's 0 for the leading order of zeta prime. there's 0 for the background. So what does the background equation look like? I just have ddt of 0 equals something plus 0, essentially. First order equation is what we want to think about. That's ddt of zeta, and zeta has only a prime part, plus zeta prime dotted into the gradient of u. What are the terms in that one? I've got zeta bar, the big zeta, which is 0. And then that one could go with either one of those, but that's 0, so we don't have to worry about that one. But what's the zeta prime one? Zeta prime dot gradient u prime. What happens to that one?
Small.
It's too small. It's a double product, so we're looking for the linear part. So the only one that we have to keep is zeta dot gradient of u. And then we play the same game over here.
Do you mean zeta prime dot gradient?
Yes. We play the same game over here and we only get the zeta prime part. Okay. Is there any variation in u away from that interface? No, so this term is also 0. Okay, so this is the vorticity equation, which, and this is actually the momentum equation, if we wanted to write the momentum equation, which goes through the same kind of logic. So, of course, Valis is non-dimensionalized, not hopefully dropping the density, but anyway. So, that's the momentum equation. This is the vorticity equation, which is just the curl of this equation, but that's basically the curl of that. Okay? Does everybody see how we're building these linearized equations? Okay, so if we have this assumption and a linearized equation, what do we do? We can just substitute. So we can plug in into there, and that turns every y derivative into a y. Oh, there should be an L there. You got that wrong. There should be an L. There should be. Oh, sorry. No, he's actually already using that. Never mind. Every time we have a y derivative, we have a y piece here. Every time we have an x derivative, we have an x piece here. Every time we have a t derivative, we have a sigma t here. And so it converts all the derivatives into things that look like this. Okay, one more subtle point is hiding inside of there. So he assumed e to the I kx plus I ly, and then he uses this one on this to write this as e to the I kx minus ky. How does that work? At least for the pressure part, he says that's true. Where is this? If I have this assumption, and then I also know that the Laplacian of pressure equals 0, how do I get from there to there?
Just by adding the coefficients that come out of the Laplacian.
Yeah, I mean, so this guy says k squared plus L squared minus, from this form, times the pressure tilde equals 0. So I can't set pressure tilde equal to 0, why not?
Pressure is not 0.
Right, I need an instability. I want something to be not 0. So the pressure is not 0. Okay, so, and neither is V and neither is U. Some of them can be 0, but not all of them. And so he's jumping over that piece a little bit. And why, so, and I can't set k squared plus L squared to be equal to 0, why not? I mean, sorry, I can't set k to 0 and L to 0, why not?
Because then it would be constant everywhere.
It would just be constant everywhere. It's not really an instability. It would be like the background flow. So the only way that we can get out of this is to say that L squared is minus K squared, which is this form. Does that make sense to everybody?
The sigma comes from CT, e to the power sigma t.
Yeah, so sigma is saying there's a potential growth or decay or oscillation. So there's not, and so it's a sigma equals C over K, if you like, if it was a propagating wave, but it might not actually really be propagating, it might just be growing in place, which is a little funny. So we'll actually need this in a second, but so this is just, I'm just taking a Fourier, a separability Fourier ansatz for what my growing mode might look like. That's what the e to the ikx plus ily plus I sigma t is. Yeah.
V prime is a vector or just a scalar?
Which one? This v?
Yeah.
This is actually the scalar. It's just the velocity in this direction. There's another velocity in the other direction equation too. This is the one that's important for getting this relationship. V prime and U prime are not unrelated. Why not?
Divergence.
Yeah, I know, if you give me one, I know the other one. Because if I have del dot U equals 0, then I have I K U plus I L Y equals 0. And then if I go through this math, I come up with something else, which looks like, I think, I K U minus K Y equals, oops, K Y, K B. Sorry, K V equals 0. So once I have U, I actually know V. Or once I have V, I actually know U. They're related like this. Okay? So where does this, before we look at the answer, which is pretty straightforward down there, where does this go wrong? What have we done that's a little fiddly here? Any ideas? So we take a Fourier basis, which, and then we plug it in. Oh, and so this is, okay, let's slow down. Why is it written this way instead of the way I wrote it over there?
It only has the real part.
It only has the real part, and it also has just an abstract function of y, which he then says is e to the minus ky. It's a little, I can assume a Fourier basis in any direction where nothing is happening, where the coefficients are independent of that direction. A Fourier basis is a complete set like that. So in the x direction, I'm just rewriting the equation by saying there's no variation in x in any of the coefficients. Like u doesn't depend on x, and u doesn't depend on time. So I can Fourier transform an x and time however I like, and this k and this c are just convenience factors that I have to worry about. That's where this comes from. This part says, well, let's abstractly say, okay, we don't know what the function is in y. And so it's a little more work to say, oh, I have this equation, and so actually the function in y has to be a decaying thing that matches with k. That's this little bit of math over here that we did. But formally, I wasn't allowed to do that right at the interface where u depends on y. I could only do it away from the interface. So the first step is assume this form. Then we notice that there's this thing happening. Then we say, oh, on this side, I don't have, u doesn't depend on y, I can do a solution up there. And on this side, u doesn't depend on y, I can do a Fourier style solution over there. That's what gets us to the form we're at here. But there's one complication, which is this little bit of, there's a little bit of magic in this. When we get to the case where the flow is sheared, we actually can't really assume that x and y are independent of each other. There's something called a non-normal mode growth that changes the problem. We'll touch on that a little bit anyway. That's sort of an oddity. Okay. So, we plug in this form then, if we agree that this form is sort of what we're going to be able to do. Why do you know what sign the minus ky is and plus ky is here? So P1 is on that direction, P2 is on that direction. How does he know if this only constrains the second derivative of y, how does he know that there's a minus sign there and a plus sign there?
Just to make it have reality or something, because it should be decreased along y to maximum, right?
Yeah, the assumption is that it can't grow towards infinity. It has to decay away from the interface. So even though if you did this more slowly and did that part more slowly, you would actually get two possible roots for L could either be plus ik or minus ik, so it could be plus ky, minus ky here. Only one of them is the one that decays away from the interface, and so that's the one that he selects. Does that make sense to everybody? Okay, so we worked hard to get this to form. We plug this form into here and we get this oddball. And then this one is a separate equation which is talking about the motion of the interface. So it's really an equation that looks like this. So it says that eta is just an advected part of the fluid. Essentially, this interface, when it moves, can't separate from the fluid. It's a material derivative. Okay? So and in this case, that's acting as a boundary condition between the upper part of the solution and the lower part of the solution. When we plug in all these forms into the upper part and the lower part, we end up getting the same boundary condition from both sides that looks like this. And that gives us this equation. Okay, so there's a lot of linear algebra, a lot of fiddliness. One of the things that I don't like about the linear instability theory is that it's deceptively powerful. We could really do a lot of linear theory like this. It looks a lot like quantum tunneling or something like that. But why is quantum tunneling different than this setup? Why is it from a physics perspective? If I use quantum mechanics, they do all this theory for whatever, the Rutherford atom and all those things. They're all like this. Why is it different in this game? What kind of equations are the equations of quantum mechanics, the Schrödinger equation?
Linear.
It's linear. So here, we can do a lot with the linear theory, but actually the real flow we're studying is nonlinear. So even though we can work hard on the linear instability theory, and we probably could have we definitely could have a semester-long class on linear instability theory, it's actually not very interesting because it doesn't tell us much about the real fluids because they are nonlinear at leading order, and specifically turbulent fluids are nonlinear ones. So I'm trying to gloss over the linear instability aspects of this, but give you a hint as to how it works. So we're going to move quickly on to turbulence from here. Okay, but anyway, so here is the condition. I can also satisfy this equation and this equation by setting V and P and eta to 0. Why is that not interesting? Yeah, there's no perturbation. So in the linear instability terminology, we are seeking a non-trivial solution to this kind of homogeneous differential equation. It's homogeneous because everything in this equation depends on one of the flow variables. I always have the trivial solution in a homogeneous system of setting them all to 0. I don't want to do that because I'm actually solving for something that's non-zero. So I'm looking for an additional condition which allows my set of equations, of which this one is one example and this boundary condition is another example, to be simultaneously satisfied without the setting all those amplitude functions to 0. I want to make a condition on C and K, and here is a condition on K and sigma, and C also for this condition. So in the linear instability lingo, this is an eigenvalue problem. We are looking for an eigenvalue of the system. In the wave description, this is called a dispersion relation. So this is the dispersion relation for this system. But those are the same thing. Eigenvalue problem, dispersion relation, they're the same thing. They mean I'm looking for a non-trivial solution to a linear set of equations that allows me to satisfy a whole mess of homogeneous linear equations all at the same time. I can do that if I have this condition satisfied. Does that make sense to everybody from the math side? Okay, so what does this mean? Sigma squared, what is sigma squared playing? What's the role that sigma is playing in our system? If sigma squared is non-zero, what does that say about this pressure field? It could decay or it could exponentially grow. Either one, right? We got positive and negative roots of this system. K squared, what is K squared measuring? It's measuring the wavelength in this direction and the decay scale in that direction. So the faster the wavelength is, the faster the decay is. So that's part of the system. The slower the decay, longer the wavelength, the farther away it reaches into the fluid, away from the interface. And now, which mode is growing the fastest? If U is given to us, right? We know what that is. But which mode is growing the fastest?
So the longer wavelength.
Careful. Longer wave number.
Longer wave number.
The bigger the wave number is, the faster it grows. So the fastest growing mode is the smallest thing. So this problem actually has what's called ultraviolet catastrophe. The smallest thing is the fastest growing thing. So if you're looking for the fastest growing thing, it is the smallest. The smaller you get, the faster it grows, and so on and so on and so on. So, and in fact, there's no condition for which this system is stable. It's always unstable to something. So what could we do in this system that would make it stabilize it a little? How can we bring a little more physics back into our original equations and damp the instability?
So it's unstable because sigma has a positive number?
Yeah, so if we were matching an arbitrary initial condition with an infinitesimal perturbation, we would have both a positive sigma and a negative sigma, and the positive sigma would grow to infinity. And it wouldn't actually go to infinity, it would grow to finite amplitude, at which case the linearized system is no longer useful. So all it tells us is that there's a growing instability. Doesn't actually tell us much about the evolution once it gets to finite size. Does that make sense, sort of? Yeah, and we can't throw out the positive and negative roots. Well, we could throw out the positive root of sigma, but we don't actually have a reason to here. We threw out the growing to infinity root as being unrealistic, but we don't throw out the one in time as being unrealistic because we actually know that this system only applies for finite amounts of time, right? If we had put walls out here, then we would have not. So if we had made our domain finite, we actually would not have been able to throw out the other root of this because it would have been possible to have that other root. We'd have to work a little harder. So because we're imagining that this starts from some instant and then becomes nonlinear some instant later, we actually have implicitly put a bound on our time variable, which means we can't throw out the growing solution. Does that make sense? That's a little bit strange. Okay. But what could I have put in this equation that would have made this maybe not blow up at all length scales? What works more on small length scales and less on big length scales? In the equation, in the momentum equation. What's missing?
Viscosity?
Viscosity. You can actually do this problem in the viscous limit, and what you find is that there's actually is a fastest growing wave number, which is the one that is as small as you can get without being overwhelmed by viscosity. So there is, in a viscous fluid, And you could actually set this up with maple syrup or something, and you could actually predict the unstable mode based on the viscosity, and it would slowly grow. You could watch it in the lab. Does that make sense to everybody? Okay. All right, Kelvin-Helmholtz down. There's a slightly different version of Kelvin-Helmholtz where we put density. We make this side, we do this with this being the vertical direction, and we make this a denser fluid and this a lighter fluid. Similarly there, you get constraints because lifting up dense stuff and pushing down takes more energy. So we'd have to do a buoyancy equation, et cetera, go through that whole game. That's another version of this problem you can do. And it's, yeah. So sometimes people, when they say Kelvin-Helmholtz, they're talking about that one. Okay, 2D parallel shear flow. So now we're going to consider the more general problem of just a profile of velocity, not a jump at one location. So I have a vorticity equation, we have profile. That's what the linearized vorticity equation looks like, with this z being, I don't know why, Vallis thinks that this is too many symbols, more than this, and he doesn't just put this in there. He keeps jumping back and forth. But anyway, that's what he means by z, is it's dy of u minus dy of u. So it's the vorticity that's in the background flow, z. So here we go. We've got the vorticity in the background flow being affected by the perturbation. We've got the background flow affecting the vorticity perturbation, and we've got the vorticity perturbation changing in time. And because it's in 2D incompressible, we can plug in the stream function in place of the vorticity. Y, and then now we have a function of y. This really is an abstract function of y now. It can't be a Fourier function of y. Why not? The other one, we had a decaying exponential and a growing exponential, but that was because what happened with u in this profile? We had a cusp, some complicated thing right here, but then we had it decaying with y and decaying with y that way. What allowed us to get away with that? The u doesn't depend on y as long as we stay away from the interface. So we could solve it with a Fourier transform method on either side of the interface, but not on the interface. When we have a parallel shear flow, u depends potentially on y everywhere. So we can't use Fourier in this direction. We just have to write a governing equation for this. So we don't expect to see a total Fourier solution. We expect to see an ordinary differential equation in y. But it's uniform in this direction, and it's uniform in time. So we can still do Fourier in x and Fourier in time, which is how we're going to get from the PDE to the ODE in y. Does that make sense to everybody? That that's this? So here we go. Here's our PDE, still PDE, bringing in incompressibility. So we've got the stream function, Laplacian of the stream function is the vorticity. Here's the stream function bear, which is the v velocity is the stream function dx. We plug in an ansatz. Ansatz is the German word for guess. We guess and check with this form. Plug it in there, and we get this equation. So if you want to become a lord on the basis of doing science, this is a good thing to start with. This is Rayleigh's equation. This is one of the many things that Rayleigh did that got him he was like a baron or something. I don't know. Anyway, whatever. I think he also was in the right family, so I think he had some other privilege that he was working with. But anyway, all right. Look at it. What kind of an equation is this? Like what class of equation is it? And Vallis is using subscripts here to mean derivatives in that direction. Is it a partial differential equation? Or an ordinary differential equation? Or an algebraic equation? It's a differential equation, and it's an ordinary one because all the derivatives are y's. The time has dropped out and the x has dropped out when we plug in this form. Where did it go? The x's went away because we gained a k squared by taking the x derivatives, and then that's all we got because it's Fourier in that direction. The times went away because we took time derivatives, and then we got a kc every time we took a time derivative, which gives us this c right here. But we don't have any more derivatives in time or derivatives in x left once we've made this ansatz. And here we go, Valis has already forgotten something. What do we have to do to get back to the full solution from this part?
Sum.
We have to sum over all the k's and all the c's that are available. So this is just one example of an unstable mode. It's not all the unstable modes. Okay, so, but here's Rayleigh's equation. So, and remember, this is a dispersion relation kind of thing, or an eigenvalue relation kind of thing. What are the variables in here that we'd like to solve for? If I give you a uyy, where does uyy come from? So what's uyy of that profile, for example? Second derivative with respect to y, with y direction being this direction. 0. So in that case, this one would be 0. And so then I would be solving this kind of a system with this and this. And I'd have to look for a balance between c and k that made this possible. And then that would give me a simple equation for the y dependence of the unstable mode, and I could solve it. So I have a dispersion relation that I'm looking for, and I've also still got to figure out what the y structure is. So if you give me a particular shear profile, I can tell you, I can continue pushing. But this equation applies to all profiles like that. And I could put another boundary condition on the other side, or I could do all kinds of things, but as long as there's no V, there's no pressure anomalies in the initial condition, there's just a shear flow of U as a function of Y, a parallel shear flow. Then this equation is a constraint. Okay? And if you do this again on the beta plane, which is kind of interesting to think, we could do two-dimensional shallow water on beta plane, with this being the east-west direction. Importantly, you can't do this being the east-west direction for fun reasons that are worth thinking about later. But this being the east-west direction, then you get the same equation except beta comes in right next to uyy, which sort of makes sense because uy is the vorticity of the background flow. Uyy is the y derivative of the relative vorticity, and beta is the y derivative of the planetary vorticity. So those two are partners in there. This really is a vorticity equation hiding underneath. Okay? So why do we care about this thing? I have the next slide where I hope I do. Oh, this is what it looks like when you get an instability. This is you get this wave, and so see we sines and cosines and kx, and then it starts wrapping up when it becomes nonlinear. That's the kind of evolution we're thinking about. Piecewise linear is another place where we could go. For one example, we'll come back to this next time. But what I wanted to show you was this equation doesn't tell you much about what the instability will be, but you can actually form a constraint from it that tells you if it's going to be unstable, this has to be true. So this Rayleigh equation is telling you limits on the kinds of instability that are possible. They may not be possible in particular shear flows. So next time we come back, we're going to start talking about other examples of shear flows and trying to think about how we use this equation and the energetics, it turns out as well, to start constraining when instabilities are possible and when they're not. So when they're not is kind of the more interesting case, because that says that flow will be stable. That's actually a stronger constraint. When they are, we then have to do more fancy stuff to try and figure out what they're like and figure out this dispersion relation and think about what it means. So that's, in a nutshell, the framing of how instability thinking goes. So, any questions before we quit? So let me make a couple of comments then on this homework we're going to talk about on we're going to have so this one comes this weekend or this week, this Friday is the next one, but then the one after that is like a month off because of spring break, etc. So I think I asked you to write a proposal for what your final paper would be for the following homework, but it's a good idea to start thinking about that. So before we get to Friday, I'll make some examples of what I think a proposal looks like. It's just a few sentences, like a paragraph that says like, I'm going to read this paper and I'm going to read this paper and I'm going to compare them or something like that. And so I'll make a couple of examples of what we're looking for and give you a list of papers that we can think about so you can start thinking about what you want to do. Because that will be the only thing other than homeworks that we have in the class. So it's kind of, you can think about that as we go. That makes sense to everybody? All right.